Today we will be talking about displays for embedded systems. We will be focusing on LCDs and SSDs. To give you a brief preview, these are some of the contents of the following talk. We start off with the topic of LCDs, basic components, working, pin configuration, execution, block diagrams, interfacing, advantages and some drawbacks of LCDs. Then we go on discussing about SSDs, that is 7-segment displays. Its construction, configuration, hardware, software, interface, drawbacks, and some of its application. Displays for embedded systems. Peripherals such as LCD and 7-segment displays are essential output peripherals of microcontroller-based embedded systems. Output devices like these receive digital information from an MPU, that is a microprocessor unit. This is an example of a liquid crystal display. A liquid crystal display is a flat panel display, electronic visual display, or video display that uses the light modulating properties of liquid crystals. Liquid crystals do not emit light directly. LCDs are available to display arbitrary images or fixed images which can be displayed or hidden, such as preset words, digits, and 7-segment displays as in a digital clock. They use the same basic technology except that arbitrary images are made up of a large number of small pixels, while other displays have larger elements. In LCD, liquid crystal solution is sandwiched by 2 sheets for polarizing material. It is used to display the status information or to display prompts to the user. Other displays used in embedded systems can be of 6.4 inch or 8.4 inch, etc. This image shows the front side of a liquid crystal display, that is an LCD display. Following image shows the back side of the LCD. Basic components in an LCD panel. An LCD panel, or more commonly known as a piece of glass, is constructed of many layers. The figure shows all the layers that are typically presented in LCD panels. The layered panel structure below shows the LCD panels is sandwiched between rear and the top polarizers. LCD module is made up of 2 layers of glass substrate containing a layer of liquid crystal material through which light passes, provided by the backlight. White light from the backlight passes through the LCD panel, which manipulates passage of light to form images projected onto the front of the LCD panel. The multi-layered structure of an active matrix LCD panel, because they use red, green, and blue color filters in place of phosphor dots, LCD panels are completely immune to image burn-in. Now let us have a look to typical pin configuration. Here we provide with a pin configuration table for a 16:2 LCD character display. VSS is the ground terminal, VCC positive supply, VDD is the contrast adjustment, and further all the configuration are shown in the table. LED is for backlight LED cathode terminal, and LED plus is for the backlight LED anode terminal. Now that was all about the signals and the hardware. Let us come to data, signals and execution. LCD accepts 2 types of signals. One is data and another is control. These signals are recognized by the LCD module from status of the RS pin. Now data can be read also from the LCD display by pulling the RW pin high. As soon as the E pin is pulsed, LCD display reads data at the falling edge of the pulse and executes it. LCD displays have 2 RAMs, naming DD-RAM and CG-RAM. DD-RAM registers in which position which character in the ASCII chart would be displayed. Each byte of DD-RAM represents each unique position on the LCD display. The LCD controller reads the information from the DD-RAM and displays it on the LCD screen. CG-RAM allows user to define their custom characters. For that purpose, address space to first 16 ASCII characters are reserved for users. CG-RAM stands for Character Graphics Random Access Memory. It is for storing the bit patterns for the 8 user-defined characters. DDRAM stands for Double Data Rate Random Access Memory that yields twice the data. DDRAM is where the characters to be displayed are stored. If you write the ASCII characters ABC to the first 3 positions in DDRAM, ABC will appear in the first 3 positions of the LCD. This diagram shows the block diagram of an LCD display, which consists of components like LCD controller, backlight, LCD panel, segment drivers. The following table shows the control and display commands for your future reference and will be explained clearly in a while. Now the instruction can be divided mainly in 4 kinds: function set instructions, address set instructions, data transfer instructions with internal RAM, and some others. Details of the instructions shown previously. Read data from RAM. Read 8-bit binary data from DDRAM or CGRAM. The selection of RAM is set by the previous address set instruction. If the address set instruction of RAM is not performed before this instruction, the data that is read first is invalid because the direction of AC is not determined. If the RAM data is read several times without RAM address set instruction before read operation, the correct RAM data from the second, but the first data would be incorrect as there is no time to transfer RAM data. After read operation, the data address counter is automatically increased or decreased by 1 according to the entry mode. After CGRAM read operation, display shift may not be executed properly. Write data to RAM. Write binary 8-bit data to DDRAM or CGRAM. The selection of CGRAM or DRAM is set by the previous address set instruction. DDRAM address set, CGRAM address set. RAM set instruction can also determine the AC direction to RAM. After write operation, the address is automatically increased or decreased by 1 according to the entry mode. Read busy flag and address. By making this readout operation, it can be determined if the LCD is performing some internal operation or not. If busy flag is high, some internal operation is going inside the LCD at the particular moment. To perform further operation, the data source must wait for the BF to go low. Here, the address counter value can also be read. Set DDRAM address. In 2-line display mode, DDRAM address in the first line ranges from 00H to 27H and DDRAM address in the second line is from 40H to 67H. Set CGRAM address. Set CGRAM address to address counter. This instruction makes CGRAM data available from MPU. Function set. DL stands for Interface Data Length Control Bit. DL is equal to 1 means 8-bit mode of data transfer, and if it is equal to 0, it means 4-bit mode of data transfer. N is the display line number control bit. N when equal to 1 will allow the characters to display in 2 lines, and when it is equal to 0, it will allow the characters to display in the first line only. F is the display font control bit. If it is 0, we'll use 5x8 dots format, and if it is 1, it was used 5x11 dots format. Cursor or display shift. Without writing or reading the display data, shifting right or left cursor position or display, this instruction is made to correct or search or display data. During 2-line display mode, cursor moves to the second line after the 40th digit of the first line. When displayed data is shifted repeatedly, each line shifts individually. When display shift is performed, the contents of the address counter are not changed. Display on or off control. This instruction controls display, cursor and cursor blink. Display on or off control bit. 1 means entire display is turned on, and if D is 0, it means entire display is turned off. C is the cursor on or off control bit. If 1, then the cursor is on, and if 0, then the cursor is off. Cursor blink on or off control bit. If it is 1, then makes cursor blink periodically, and if it is 0, it stops the cursor to blink and cursor looks steady if the cursor is turned on. Entry mode set. This instruction sets the moving direction of cursor and display. When ID is equal to 1, the cursor moves to the right, and if ID is equal to 0, then the cursor moves to the left. Return home. This instruction sets the address counter to 00H and returns the cursor to the first column of first line. If display is shifted previously, this instruction shifts this too. The DD-RAM contents don't change in this instruction. Clear display. Clear all the display data by writing 20H to all DD-RAM address and set value DD-RAM address counter to 00H. It returns the cursor to the first column of first line and sets the entry mode to increment mode. Now the question is how to display data in the LCD or give command to it. There are two modes of data transfer supported by LCD displays. One is 4-bit mode, another is 8-bit mode. To transfer data in 8-bit mode, first put your data in the 8-bit bus, then put command in the command bus and then pulse the enable signal. To send data in a 4-bit mode, first put upper 4-bit in the 4-bit data bus connected to 4 MSB pins of LCD display, then put control signals in the control bus. Then pulse the E pin once. Next, put the lower 4-bit in the data bus and pulse the E pin again. Here is a flowchart simply describing the same. LCD initialization. We're pretty familiar how to send data, but before displaying characters on the LCD display, it must be configured first. To configure an LCD display, 4 commands words must be sent to LCD in either 4-bit mode or an 8-bit mode. The commands are function set, display on or off control, entry mode set, display clear. Here is a flowchart of initialization sequence of LCD display in embedded systems, which shows some sequence of steps such as step 1, power up and wait milliseconds, step 2, send the function set, step 3, wait 39 microseconds and then display on or off control signal, then again wait for 39 microseconds and next step, then sneak towards next step and send entry mode as set, wait 39 microseconds and then in next step send display clear bit. Keep waiting for 1.64 milliseconds and then your LCD display is properly initialized. Application of LCDs. Since LCD panels produce no light of their own, they require external light to produce a visible image. In a transmissive type of LCD, this light is provided at the back of the glass stack and is called the backlight. While passive matrix displays are usually not backlit, active matrix displays almost always are, with a few exceptions such as the display of the original Game Boy Advance. Moving clockwise, we see an early LCD calculator, LCD wavelength wristwatch in which hours are written in negative digits and minutes will increase until 30 minutes, then decrease again until the next hour. Moving further is a green LCD watch with LCD usage in medical field chart on the right. Common implementation of LCDs. Currently, there are several common implementation of LCD backlight technology. The CCFL, 18 parallel CCFLs as backlight for a 42-inch LCD TV. ELW LED, the LCD panel is lit by a row of white LEDs placed at one or more edges of the screen. WLED array, the LCD panel is lit by a full array of white LEDs placed behind a diffuser behind the panel. RGB LED, similar to the WLED array, except the panel is lit by a full array of RGB LEDs. Some more applications. Monochrome passive matrix LCDs were standard in most early laptops and the original Nintendo Game Boy too. Positive matrix LCDs are still used today for applications less demanding than laptops and TVs. Such examples are calculators and watches. Application in the medical world. Medical displays, touchscreen displays, mobile point of care displays, surgical displays, chemical displays, patient monitoring displays, clinical review displays. Wide application of LCD. Today, industrial color LCD modules are used in a wide range of applications. The figure shows the whole spectrum of color LCD modules currently in use, grouped by screen size and resolution. While LCD modules have a history of being used for ATM and point of sale terminals and factory automation systems, they are now being used in an increasing range of applications that include special construction vehicles, marine vessels, and other outdoor equipments thanks to their enhanced luminance and low reflectivity. Demand has been growing, especially for widescreen LCDs that are better equipped to handle today's digital content and external size restrictions. Color LCD modules are also increasingly being used more for portable industrial equipment such as handheld ordering systems. Alarm clocks and wall clocks commonly use LCDs to create simplistic, easy to read screens. Modern LCD clocks use a liquid crystal display to create decorative colors and images behind the data and time. While the numbers are typically simplistic, LCD alarm clocks often offer customization options for a stylized display. Calculators use LCDs because of its light and compact design. Television. The LCD technology is common in television screens for its lightweight design and cost effectiveness. Camera display screens often use LCD technology to save space and reduce weight. Computers, desktop and laptop computer screens use LCD technology because of the compact design and energy efficiency. Watch display screens use LCD technology to create a modern watch screen. Advantages of LCDs: they consume less power, they generate less heat, saves a lot of space compared to picture tubes due to the LCD's flatness. Due to the less weight and flatness of LCDs, they are highly portable. They don't flicker and less screen glare in the LCDs, which reduces the eye strain. They are lightweight, aesthetically appealing, energy efficient, and long-term cost effective. There is a continued tabular form of more advantages of LCD in the aspect of brightness, emissions, geometric distortion, power consumption, physical aspects, screen shape, and the sharpness of it. There are some drawbacks of LCDs. LCDs cannot form multiple resolution images. The contrast ratio of LCD images is lesser than CRT and plasma displays. Due to their longer response time, LCDs show ghost images and mixing one image change rapidly. The narrow viewing angle of an LCD weakens the image quality in wider viewing angles. Here is the continuation tabular form of the more drawbacks of LCDs in aspects of aspect ratio, black level, contrast, color and grayscale accuracy, cost, grayscale, motion artifacts, resolution, viewing angle, white saturation, bad pixels, and interference. The 7-segment LED display. The red timer thing is the LED based 7-segment display which cycles through the common glyphs of the 10 decimal numerals and 6 hexadecimal letter digits. Now we start on the topic of 7-segment displays. We start with what is a 7-segment display. A 7-segment display is a set of 7 bar-shaped LED, that is light-emitting diode or LCD elements arranged to form a squared of figure 8. A few 7-segment displays use other illumination devices such as incandescent or glass plasma. It is used to display BCD digits 0 through 9, a group of 7 LEDs physically mounted in the shape of the number 8, plus a decimal point. Each LED is called a segment A through F. Its construction. 7-segment displays can be constructed using any of a number of different technologies. The 3 most common methods are fluorescent displays, the liquid crystal displays, and the LEDs. This picture represents the 16x8 grid showing the 128 states of a 7-segment display. Something more about the SSD. Individual 7-segment display packages are available from a variety of vendors. Some 7-segment displays include a decimal point. Some displays have even more dot-shaped elements to portray time or temperature in hour and minute format. Its history. The 7-segment concept is more than a century old. One of the earliest records of its use dates back to an electric power point in the year 1910. That display comprised a large matrix of incandescent bulbs arranged in 7 rows. The bulbs could be switched on and off row by row to inform engineers about the condition of the system. There are 2 configurations of SSDs. One is the common cathode and second is the common anode. We will start off with common cathode. All nodes are connected together to a power supply. Cathodes are connected to data lines. Logic 0 turns on a segment. As shown below, all the anode segments are connected together. Power must be applied externally to the anode connection that is common to all the segments. Then by applying a ground, the appropriate segment will light up. An additional resistor must be added to the circuit. Second, we come to common cathode. All cathodes are connected together to ground. Anodes are connected to data lines. Logic 1 turns on a segment. 7-segment displays are usually driven by a special type of IC commonly known as a 7-segment decoder such as the CMOS 4511. This 7-segment display driver, which is known as a binary coded decimal display decoder and driver, is able to illuminate both common anode or common cathode displays. The 74LS75 latch. A latch is a chip that stores data values. 75 latch has 4 flip-flops, store 4 binary values. Each chip enabled signal controls a pair of the flip-flops. A latch is present at each display decoder so that the appropriate values are only displayed on the LED while the chip enable is high. The 74LS47 decoder. This is a display decoder chip that is used to decode the 4-bit binary number that is sent to it. The chip decodes the 4-bit signal to appropriate 7-bit signal using logic circuits inside the chip. The decoder has 4 inputs D, C, B and A, which represents a binary value such as 0101. The 4 bits of the binary number each represent a multiple of 2. From left to right, the bits represent 8, 4, 2 and 1. Now we go on to the hardware of the 7-segment display. The 7-segment display boards have been constructed in order to reduce the time and effort needed. Figure 1 shows the schematic of wiring diagram used for the construction of these display boards, which can be modified in various ways for additional 7-segment components to be added. Software of the 7-segment display. After the hardware is constructed, the software needs to be written to control these displays. The low 4 bits are the binary number to be displayed, while the high 4 bits are used to enable the desired displays. The enable opens the latch of the appropriate display. When the enable bit is set low, the display then latches on the data and display circuit will remain unchanged until the enable is set high again. As shown in the figure, the 8-bit output port is broken into two parts. Example shows conversion of 000010101 in binary to decimal, that is 21 in decimal number. The given example in the figure will display a 5 on the display enabled by P3.4. First the display is enabled and then afterwards it is disabled. This shows the truth table for BCD 7-segment decoder display. Now, this figure shows how to interface 7-segment display to a microcontroller. Consider we have to display 1 from the above figure. We have to know that turning on segment B and C will show 1 on the 7-segment display. So P2.1 and P2.2 should be logic 0, whereas rest of the pins should be logic 1. The figure table shows the lookup table for CA display, that is the common anode display. We can now interface a single 7-segment to the microcontroller, but for interfacing multiple 7 segments, we use scanning principle where one 7-segment is displayed after another, but this process is very fast, hence the flickering cannot be seen by human eye. Figure 3 shows the circuit for interfacing two 7-segment displays. When interfacing more than one 7-segment display, the segments of all displays are connected together, whereas their anode are switched on one after another. For a 7-segment display, we can produce a truth table giving the individual segments that need to be illuminated in order to produce the required decimal digit from 0 through 9 as shown in the truth table. Now there are some applications of 7-segment display. The first is remote induction motor controlled by Android application with 7-segment display. Speed control of an induction motor such as fans by a tri-interfaced microcontroller through remotely operated commands to it in steps by touchscreen based user-friendly GUI on any smartphone, and with Android applications displaying status through 7-segment display. For gasoline price totems and other large signs, 7-segment displays made up of electromagnetically flipped light reflecting segments are still commonly used. 7-segment display are also used as watches and earlier calculators. On the left side, you can see a multiplexed 4-digit 7-segment clock display with only 12 pins, and on your right is the 7-segment display calculator. There are some particular drawbacks of a 7-segment display. Displays with more segments yield a much more realistic alphabet. The 7-segment display does not allow the true descenders on letters such as G, J, P, Q, and Y. It also does not allow diagonal strokes on letters. The boxy nature of the 7-segment display would also make letters such as 0 and D and the number 0 indistinguishable. There are displays to avoid these problems such as a 16-segment display. Here is the end of our presentation. This presentation is given by Himanshu Duggal and Prachi Chaudhary.